we spoke about a current affecting the compass. So basically, it is because of what? It's because of it can produce a magnetic field. Now, regarding the direction, so you can see there's a deflection when you switch it on. When we change the current direction, that is, if I make it move from say left to right and then from right to left, there's a change in direction. That's the deflection will move in a different direction. And here I've not shown if I increase the amount of current or decrease the amount of current, the amount of deflection also varies. So basically the strength and the direction is not fixed. Now, how can we determine that? It's with the help of this particular law. This is based on two people, Biot and Sawat. Again, my pronunciation might not be right. High probability. So this is a rule book for finding the magnetic field line around a wire carrying current. Simple. You have a wire, you have a current, and you have a point. You're looking at a point P. So because of this small length D over here, right, a point P which is say R units away at an angle of theta will have some push or pull if there is a compass, right, in a particular direction with a particular amount. And this particular law helps us in looking into the strength and the direction aspect of this. Okay, guys, it's a very simple thing. So the statement is like this according to the law. So we have a magnitude of magnetic field dB. Oh, by the way, we use B to represent your magnetic field. Anything to do with magnetic field, we use B. So basically B will be your magnetic strength, field strength. That is nothing but magnetic force. Okay, now moving on. So according to the law, we have things directly proportional to the current, that is your magnetic field dB is proportional to the current, directly proportional to length dl. See this small length dl. It makes sense, right? The current I and the small length dl and the angle. Okay, so it's proportional to sine theta, where theta is the angle between the current element and the position vector. This is your current element. Current element, a small one. And your current itself. And finally, it is inversely proportional to square of the distance. So when we combine all of this, what do we end up with? That dB is proportional to first thing is current, then dl, then sine theta, and inversely proportional to the square of the distance. So when we open this proportionality symbol, we will get a proportionality constant mu naught by 4 pi, where what do you think mu naught is? Think about it. So I dl sine theta by r square. What is mu naught? Yes, it would be proportionality constant, and this is nothing but your permittivity of free space. Permeability of free space and same stuff. So basically, it does get affected by the material around. Again, same funda as your correct electrical field. That's it. There's a lot of pattern, guys. If you see the pattern, it's quite simple. Okay, so that's your first part. Now we have to expressing in terms of cross product. Because this will give us a magnitude, but whatever direction. So to help us with that, we'll multiply and divide r. Okay. So I dl sine theta by r square. I'm not writing the statement that I'm multiplying dividing with r. Being your position vector, the length and all of that. So when I look into this term, r dl sine theta, right? R dl sine theta. What does it look like? It is dot product, right? No, it is cross product. Again, if you're not familiar with this by now, at this stage of your education, you have to go back to vectors. Actually, any point of time in this 2 grades and in the future, if you're not able to understand cross and dot, you have to go back to basics. Okay. And so it is always measured from dl to r, and this is r cube. There are many ways of representing it. You can use a unit vector over here. This will become square and all of that. So if you guys want to see that, again, be good with vectors. We can't stop for every explanation. So this is another expression that you might see. Just that here it is unit vector. It's in unit form. Okay. And so this is square, right? So yeah, I mean, TK, we got cross product, but where is the direction? Literally, where is the direction? Well, the direction again is over here. So what we have to do is open your hand, right hand that is. So this has to do with your right hand. You have to have your thumb in the direction of the current. Magnetic field and your finger, sorry, not magnetic field. The point, right, position vector should be in the direction of your fingers per se. And when you curl your finger, or what I do is, actually, I make my students do this. Of course, you guys are also my students, so you should be doing this. So what is that? In between curling and opening your palm, it's in between that, right? So let me show that for you guys. Something like this. So when we do this, right? So basically it is pointing upwards, is it not? So that will be your direction over here. Ideally, we have to kind of curl it, right? Make it into a fist. So that will give us the entire set of directions everywhere. Okay, guys. So you might not have exactly got everything what I've just told. So let me read through. The direction of the magnetic field as per the law is determined by your right hand. So point your thumb in the direction of the current. That's very simple. Point your finger in the direction of the position vector from the current element to the point where the field is being calculated. So in this case, it's over to the right. Curl your fingers, right? Make it into a fist. The direction of which in which your finger curls represent the direction of the magnetic field. So let me put it this way. Okay, there are special cases over there. Yeah, say we have the wire over here, and say we have the current. I'll take it in this direction. Now you should have your thumb in this direction, okay, as per the diagram. Say we take a point over here. So what did I tell? I am asking you guys to just do this. Yeah, that's a good diagram. Better to get an idea. So it's pointing over here. Is it not, guys? So it's pointing upwards. See, the point is above the wire, right? This is above. Then again, same funda, open your finger. Let me draw this again. Again, you guys can, I mean, actually, you guys should be knowing this by now. So again, we'll open a palm to the position vector. Your thumb is pointing to the right. Again, this is open palm, by the way. Then curl your finger. I tell just bend it in this way. So it's pointing towards the left. So basically, it's going round and round, right? Just take the tangent over there. So the circle in this case is in, what is this? Anti-clockwise. So take the tangent and that will be above, it will be to the left. On the right, it is up. On the left, it is down. And the bottom is to the right. Okay, it's as simple as that. Now, what if we have the angle or the wire and the point, right? DL, the small length, and the position vector in the same direction. So basically this parallel or anti-parallel. The point on the axis of the current element. So if it's on the axis. So basically this leads to theta is equal to what? Clearly 0 degree or 180 degree. And we know that sine of either of these values, right? Let me take the 0 value, is nothing but 0 itself. Sine 0 is 0. Therefore, dB will be equal to 0. We'll talk about the unit in the next video, I guess. Now, what if we have it at perpendicular? That is theta is equal to 90 degree or 270 degree. So it's basically ends up being positive or negative, but dB is maximum in this case because sine theta is sine 90 degree is equal to 1. Of course, in terms of sine 270, which is minus 1, but in the opposite direction, that's all. But its strength is maximum. Maximum strength, let me write that off. Maximum strength. Okay, so very simple set of things. We understand that this guy can get affected, the compass can get affected by the current in the wire. It can get affected, of course, when we talk about compass, direction is pretty much important, and how much deflection. So these two factors, force and the magnitude. Sorry, magnitude and the direction. These two factors has to be studied, and that is studied with the help of your Biot law, Biot-Savart law. So all it tells is, if you pick up the smallest of wire part over there, look at the current going through it, and look at the angle between your current element and the position vector, and look at the distance. So all of this put together, you get this formula, and bit of a rearrangement when you get your cross product. Okay, and finally, we're looking at the direction. When it comes to direction, you have to use your right hand. Point your thumb in the direction of the current. Point your palm in the direction of the point, or point your fingers in the direction of the position vector. When you try to curl, whatever direction the finger points to, that will be a direction of your magnetic force. Okay, so you have to write it down now.